Harmonic input. In the previous two lectures, we saw how systems, first order and then second order systems, responded when we put a unit step function in as our input. In this lecture, we're going to look at a different input, specifically a simple sine or cosine, or collectively we can call that a harmonic input. At the end of this lecture, you should be able to read a log scale plot either by hand or using MATLAB. You should be able to use a Bode plot to determine the magnitude and phase of an output signal. You should be able to find the closed form steady state solution for the output of linear systems that have a cosine or a sine as the input, and also use normalized Bode plots in order to design our systems so that they don't operate near resonance. So as I said before, we only looked at step inputs into our systems, but now we're going to look at these harmonic inputs with a constant angular frequency. So at the bottom we have here a little schematic of the systems we're going to be looking at. We still have this transfer function, g, that's coming from that modeling phase, and we're going to limit our analysis to linear systems, as we've been doing this entire semester so far. So the idea here is that if our input into this linear system is some here I have a sine omega t, where omega is constant and a is constant. This could also be a cosine, but here I'm illustrating it with a sine function. I have some sine function coming in with some magnitude and some frequency. It goes through the transfer function, and then I get my output on the other side. My output at steady state is going to be b sine omega t plus phi. So once I reach steady state, my output is going to have the same frequency, omega, as my input. However, the magnitude is going to be different, and it might be out of phase with my input. More about the phase in a couple of slides here. So we have a couple of definitions here. The ratio of the output amplitude to the input amplitude, that b over a, that is what we're going to call m, the magnitude. And this phi is our phase that comes in our output. So what we're going to see is when we reach steady state, our output can be attenuated, which means that m is less than 1, which means that the output amplitude is less than the input amplitude, or it can be amplified, m greater than 1, so b would be greater than a. And we could have a phase shift right or left. This is meaning that the phi value could be positive or negative, but always it's going to have the same frequency as the input function. But we're going to be interested in how do we know what the output amplitude and phase are going to be. And interestingly, m, the magnitude, and phi, the phase, are going to be dependent on the input frequency. So it's not going to be the same regardless of what our input is. A faster frequency or a slower frequency is going to change what the output phase and the output amplitudes are. And again, I want to stress that this is talking only about steady state behavior. That means as a lot of time passes by, after we've put this input into our system, our output is going to take this form, this b sine omega t plus phi. However, before steady state, we're going to have what we call this transient phase, where it's not going to be behaving as this simple sine or cosine function on the output. Now, in vibrations, we're going to be calculating what's happening during this transient phase. We're going to be simulating it when we use Simulink or other methods to solve our systems in this course, but we are not analytically going to be finding the function during the transient stage. We're going to save that again for next semester. So if we know what our input is doing, if we know what the magnitude m is, and if we know what phi is, we are going to be able to predict our output. But one thing we have to do first is, well, we have to find out what is m and what is phi. So two kind of branches this can take. The first is if we have like a real system and we don't know the transfer function, we haven't modeled it yet, but we know that we can measure input into it and output out of it, then experimentally we could determine what the transfer function, what the magnitude and what the phase are, because we could put a known input in at some known frequency and some known amplitude, and then we can measure what the output amplitude is and what the phase lag is, or what that phi value is. And we can do this for a range of input frequencies, omega, and we keep measuring what the output looks like. And experimentally, we could see what the relationship is between the input frequency and the magnitude and the phase. In this course, we're not going to be doing this, but it is possible in a real system to get that relationship. We'll be looking at analytically, But in an experimental course, you might be interested in doing this for some system that you either can't model or have not modeled. Instead, in this course, we are going to be looking at it analytically. We're always going to know the transfer function ahead of time. That is to say, we're always going to make a model of our system, generate that transfer function, and then with that, we're going to analytically be able to calculate our mass, our magnitude, and our phase. So again, that ratio, the output amplitude over the input amplitude, is called the magnitude. And if we take our transfer function g, and now a little bit different than what we saw before, we put, instead of g of s, I'm going to replace the s with j omega. So j is the square root of -1, and omega is the frequency. And we'll see in the forthcoming example how this is going to work. But the magnitude, that relationship of b over a, is going to be the absolute value, or really the magnitude, of that transfer function g when we evaluate it at j omega. And then the phase, again, a function of omega, is going to be the angle of transfer function g evaluated at j omega.